From this lecture, we will start number systems. Number system defines a set of values used to represent quantity. Let us consider any quantity, and this quantity is represented by decimal number 7392. This is in decimal. We can also represent the same quantity in any other number system like binary, octal, duodecimal, hexadecimal. The decimal number system is the most popular and common number system which we use in our daily life. If we have to measure the distance, weigh something, or count our money, we use decimal number system. There are 10 different digits in decimal number system from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 different digits in decimal number system. In case of binary number system, we have 2 different digits, and 2 is the base for binary number system. Now what is this base? The base of a number system is also called as radix. The base is also called as radix, and because of this r, the notation for base is a small r. Now the base will tell us how many distinct digits we have in a number system. For example, in case of decimal number system, the base will be 10 because we have 10 different digits in decimal number system. For binary, we have 2 different digits. Now what are these 2 different digits we have to find? The digits will start from 0, and there will be increment of 1 every time, and it will end to r minus 1, where r is the base, and in this case r is 2. So 2 minus 1, this will give us 0 and 1. So there are only 2 digits in case of binary number system, and in binary number system we do not call them digits but we call them bits. And as there are 2 numbers, we call this system binary number system. In case of octal, the base is 8, so we definitely have 8 distinct digits in case of octal number system, and they are from 0 to 8 minus 1, and this will give us 0, 1, 2, 3, 4, 5, 6 and 7. So these are the digits in case of octal number system. For decimal, we have already seen 0 to 9, 10 distinct digits. For duodecimal, the base is 12, so we have 0 to 12 minus 1, and this will give us 0, 1, 2, 3, 4 all the way to 9. And then we have A. We represent 10 as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. This is how we represent 10, 11, 12, 13, 14 and 15. So 10 is A, 11 is B, and we only have 12 distinct digits from 0 to 11, so we will have 0 to B in case of duodecimal number system. For hexadecimal, we will repeat the same process. 0 to 16 minus 1. 16 minus 1 is 15. So we have 0 to 15. So 0, 1 all the way to F, because F is 15. This was the small introduction on number systems. In the coming presentations, we will see more details on them. We can also have a number system with base 4. We can have base 4, and in this case, we have 0 to 4 minus 1. So we have 4 distinct digits, and they are 0, 1, 2, 3. Very simple. So if we know the base, if we know the radix, a small r, we can definitely find the different numbers in the number system. Now we will move to next part of this presentation, in which we will discuss weighted and unweighted codes. The number 7392 can be written as 7 thousands, 3 hundreds, 9 tens and 2 ones. This is how we can write this number. Or I can write 7 multiplied by 10 raised to power 3, 3 multiplied by 10 raised to power 2, 9 multiplied by 10 raised to power 1, and 2 multiplied by 10 raised to power 0. This is how we can write the number 7392. The weight of this position is 10 raised to power 0. The weight of this position is 10 raised to power 1. Weight of this position is 10 raised to power 2, and weight of this position is 10 raised to power 3. Generally, the coefficients 7, 3, 9, 2. These are the coefficients, and generally the coefficients are written and the power of 10 is determined by their position. The number system with weights on position we call weighted number system, and the number system in which there is no weight on the position we call unweighted number system. So the number system and codes we can categorize into two groups. The first one is weighted and second one is unweighted. In weighted we have few examples. First one is decimal number system that we have seen here, the decimal number system. The second one is binary, of course, octal, binary coded decimal, etc. These are the examples of weighted number system. Examples of unweighted system are gray code, XS3 code, etc. So this is how we can classify the number system and codes depending upon the weights on position. Now we will move to the next part and the last part of this presentation, in which we will compare binary, decimal, octal and hexadecimal number systems. Let's say there is a quantity. We are representing this quantity in a number system with base R1. R1 is the base of number system, and let's say capital N1 is the total number of digits, required to represent this quantity in this number system. Let's say there is another number system. We are representing this quantity in another number system, and the base for this number system is R2. Capital N2 is the total number of digits used to represent this quantity, and for an instance, let's say R1 is smaller than R2. The base R1 is smaller than the base R2, then capital N1 is greater than capital N2. This is very important point. When we increase the base, when base increases, the digits required to represent the quantity decreases. For example, 7392 is the decimal number which is used to represent the quantity. Then in binary it is represented, the quantity is represented by 11100110000 in binary. So you can clearly see the number of bits are way more as compared to the number of digits in decimal, because base of binary number system is 2 and 2 is smaller than the base of decimal number system. If I represent the same quantity 7392 in octal, then I will have 16340. This is in octal. We definitely have reduced the digits as compared to the binary number system, but we still have more digits than the decimal number system. In decimal we are having 1 2 3 4 4 digits, and in octal we have 1 2 3 4 5 digits, because in octal number system the base is 8 and still 8 is smaller than 10. Now we will represent the same quantity in hexadecimal. In hexadecimal it is equal to 1CE0. This is in hexadecimal. Now there is one important thing that you can see. Here we have 4 digits, and in this case also we have 4 digits. So we can say that N1 is not strictly greater than N2, but they can be equal. In the last presentation, I introduced binary number system to you. From this lecture, we will start conversion part of our number system. The first conversion that we have to study is decimal to binary conversion. We have two methods to convert a decimal number to binary, and we will start with first method. Let's say the decimal number is 13 and we want binary equivalent of 13. If you remember the last presentation, I introduced positional weights for binary number system. Let's say the number is B0, B1, B2, B3. These are the bits of binary number. Then the weight of this position, the 0th position, is 2 raised to power 0. Weight of this position is 2 raised to power 1. Weight of this position is 2 raised to power 2, and weight of this position is 2 raised to power 3, right? And 2 raised to power 0 is equal to 1, 2 raised to power 1 is equal to 2, 2 raised to power 2 is equal to 4, and 2 raised to power 3 is equal to 8. We can also have 2 raised to power 4 equal to 16, but we do not require 2 raised to power 4 because the number in decimal is 13. We want to convert 13, and 16 is greater than 13. So we do not require 2 raised to power 4. And out of 1, 2, 4, 8, the number closest to 13 is 8. So we can write 13 equals to 8 plus 5, right? 5 is not there. We are allowed to select from 1, 2, 4 and 8. We have selected 8. Now we have to select number closest to 5, and the number is 4. So 5 we can write 4 plus 1, and fortunately 1 is there. So 13 we have to write 8 plus 4 plus 1. And now we have to find out the values for B0, B1, B2 and B3, and it's very simple. You can clearly see 1 is 2 raised to power 0 and it is included, so B0 is going to be 1. 2 raised to power 1, which is 2, is not there, so B1 is going to be 0. 2 raised to power 2, 4 is there, so B2 is going to be 1, and 2 raised to power 3, 8 is also there, so B3 is also 1. So the binary number is 1101. The binary equivalent of 13 is 1101. This is the first method to find out the binary equivalent of a decimal number, but this method is not preferred. We will have another method, another simple method to find out binary equivalent of a decimal number. In this method we have to divide the number by 2 to convert decimal number to any other base. R, in this case R is equal to 2. We have to divide the integer part by R and multiply fractional part by R. First we will see example in which there is no fractional part. Then in next example we will solve one problem in which there is fractional part. So for the first example of method number 2, we don't have the fractional part in the decimal number. And let's consider the same scenario. The number is 13. Okay, now we have to divide 13 by 2. So we will do this quickly. (13) and 2. 13 is dividend and 2 is divisor. When we divide 13 by 2, we have 6 and the remainder is 1. Now this 6 is quotient and 1 is remainder. 6 is quotient and 1 is remainder. We again have to divide the quotient by 2 and the result is 3 with remainder equal to 0, and we will continue the same process. We will divide 3 by 2, quotient is 1 and remainder is also 1. We will again divide 1 by 2, quotient is 0 and remainder is 1. We have to repeat the process until we have quotient equal to 0. When we have quotient equal to 0, we will stop, because when you try to divide 0 by 2, you will have quotient again equal to 0 with remainder equal to 0, and the process will repeat, and every time you will get remainder equal to 0. The remainder will give us the binary number, but there is one twist. We have to start looking from bottom. 1 1 0 1. As we have already seen the binary equivalent of 13, the answer is 1101. So don't consider this one as MSB. If you consider this as MSB, the result will be 1011, which is not true. So this one right over here is the MSB, the most significant bit, and this one, the first one, is LSB, the least significant bit, and MSB is the leftmost bit, so we have one here, and LSB is the rightmost bit, so this one comes here. So this is the binary equivalent of number 13. We have to start looking from bottom and we have to go up like this. So this is the second method, and result is obviously 1101. This is most preferred method to convert decimal number to binary. Now we will consider another example in which we have fractional part also. The number is 25.625. This is in decimal, and we want binary equivalent of this number. So what we have to do, we have to divide the integer part by 2, and we have to multiply the fractional part by r. And in this case the integer part is 25, this is integer part, and 625.625 is the fractional part. So we will do this quickly because you already know the concept. We will have 12 as the quotient, 1 as the remainder, 6 0 3 0 1 1, and finally we have 0 1. So the binary equivalent for 25 is 1 1 0 0 1, because we have to look from bottom to up. So this one is MSB and this one is LSB. 1 1 0 0 1. Now we have to solve for fractional part. The fractional part is 0.625, and we have to multiply 0.625 by 2, and this will give us 1.25. Now listen carefully what we have to do. We have to consider this integer part 1.25 we have to consider, and we have to take it out, and once we have 1 taken out we have 0.25 left, and we again multiply 0.25 by 2, and the result is 0.50, and now we have a 0, so we are left with 0.50. 0.50 multiplied by 2, and this will give us 1.00. We will take this one, and finally when 0.00 is multiplied by 2, 0.00 is multiplied by 2, we have result as 0.00, and this 0 you can take out, of course, and when you repeat the process you will have bunch of zeros. And when we have to consider these ones and zeros in the result, we do not go from bottom to top, but we go from top to bottom. We will go from top to bottom. We will consider this 1, then this 0, then this 1. So we have 1 0 1 0. You can consider this 0 and so many zeros after it, because it will not change the result. In the same way, when you consider this 0 and all the other zeros following it, you will have more zeros before this 1, and these zeros will not change the result. So we do not include them in the answer. Our answer is 11001.101. This is the binary equivalent for number 25.625. So there are two important things that you must know. In case of integer part you have to go from bottom to top, and in case of fractional part you have to go from top to bottom. Here you have to divide it by 2, and in this case you have to multiply it by 2. Now we will move to homework problem. There are two homework problems. First one is 67 in decimal, and you have to convert it to binary. The second problem is 129.75 in decimal, and you have to convert it to binary. Once you have your answer, post it in comment section, and we can definitely fill the answer here, 11001.101. This is all for this presentation. If you have any doubt, go ahead and ask. See you in the next one. In this presentation, we will learn octal to binary and binary to octal conversion. There are 8 different digits in octal number system. If you remember the first presentation on number systems, I told you base in case of octal number system is equal to 8. So R is equal to 8 in octal number system, and hence we have 0 to 8 minus 1 different digits in octal number system. it means 0 to 7. I have already written the digits in octal number system 0 to 7, and each one of this can be represented by equivalent 3-bit number. The most important part of this presentation, that we can represent each one of these by equivalent 3-bit number. 0 I can represent by 0 0 0 3-bit number. 1 I can represent as 0 0 1. In the same way, 2 will be represented as 0 1 0. 3 we can write 0 1 1, 1 0 0 for 4, 1 0 1 is for 5, 1 1 0 is for 6, and 1 1 1 is for 7. So this is how we can represent the 8 octal numbers by an equivalent 3-bit number. This will be more clear when we solve one example. First we will see octal to binary conversion. The octal number is 37.45. This is in octal, and we want the binary equivalent of this number. From this table we can write 3 as 0 1 1. 3 we can write 0 1 1. 7 we can write 1 1 1. So 1 1 1. Now we have point here. 4 we can write 1 0 0, 1 0 0. 5 we can write 1 0 1. So binary equivalent of this octal number is 0 1 1 1 1 1 point 1 0 0 1 0 0 1 0 1 1 0 1. This is the binary equivalent of this octal number. It is very easy to convert octal number to binary. We will see one more example on this. The second example, the octal number is 22.07. This is in octal, and we want binary equivalent of this octal number. 2 we can write 0 1 0, so 0 1 0. Again we have 2, so I will write 0 1 0. Then we have point. 0 is written as 0 0 0, and 7 we can write 1 1 1. So this is the binary equivalent for 22.07. Now we will move to binary to octal conversion. The next part of this presentation is binary to octal conversion. Let's move to first example. The binary number is 10110.11. This is the binary number, and we want octal equivalent of this binary number. We will again use this table. Binary to octal conversion is little bit tricky as compared to octal to binary. In this case we have to make group of 3 bits, and first we have to locate the binary point. This is the binary point, and for integer part we have to move from right to left, and for fractional part we have to move from left to right. In first group we have 1 1 0. In second group we have 0 1 0. I can add 0 here to make this 3-bit. Adding 0 here will make no difference in the number. So this is the first group, this is the second group. We have group of 3 bits, and now we will move to fractional part. We have to start from left and we have to move to right. So the first group for the fractional part will have 1 1 0. Adding 0 here will make no change in the number. Now I will use this table. 0 1 0 is 2, 0 1 0 is 2, so we have 2. 1 1 0, 1 1 0 is 6, so we have 6. Then I have point, and 1 1 0 is again equal to 6, so we have 6. So the octal equivalent of this binary number is 26.6. Now we will move to second example. The second example, the binary number is 1001.1. This is in binary, and we want octal equivalent of this number. For integer part we will start from right to left. In first group we have 0 0 1. In second group I will add 2 zeros, and we have 0 0 1 again. For the fractional part I will add 2 zeros. This will give me 1 0 0. 0 0 1 is 1, and 1 0 0 is 4. So 11.4 is the octal equivalent of this number. I am adding zeros to have the group of 3 bits. You can also add 3 more zeros, and this will be The third group of the integer part, 0 0 0, will give us 0. This 0 will make no difference, so it is redundant to add this 0. This is all for binary to octal conversion. Now we will move to homework problem. In first problem, the octal number is 672.13. This is in octal, and you have to find the binary equivalent of this octal number. In the second problem, we have binary number 10111.1001. This is the binary number, and you have to find the octal equivalent of this binary number. So this is all for this presentation. See you in the next one. The last type of conversion is hexadecimal to octal and octal to hexadecimal conversion. We already know how to convert hexadecimal number to binary and binary number to hexadecimal. We also know how to convert octal number to binary and binary number back to octal. If you want to convert hexadecimal to octal and octal to hexadecimal, the direct conversion is not possible. You cannot convert octal to hexadecimal directly or hexadecimal to octal directly. So we have to follow this path. If you want to convert hexadecimal to octal, first you have to convert it to binary, then you have to convert this binary number to octal. And if you want to convert octal to hexadecimal, you have to repeat the process in reverse direction. This will be more clear when we solve few examples. So example number 1. In first example, we want to convert hexadecimal number CAD to octal. And as you can see, if you want to convert hexadecimal to octal, first you have to convert hexadecimal to binary. So we will convert CAD to binary first. C is nothing but 12, and 12 is represented by 1100, right? 12 is represented by 1100, the 4-bit equivalent binary number, and A is 10, and 10 is represented by 1010. The next number is D, and D is 13, and 13 is represented by 1101. So this is the binary equivalent for CAD. So we have done the 50% job, and now we have to convert the binary number to octal. So we will convert this binary number 110010101101, this binary number, to octal. And if you remember, we have to make group of 3 bits. So we will start from right. This is the first group. This is the second group, this is the third group, and this is the last group. In first group we have 101. 101 is equivalent to 5, so we have 5. In second group again we have 101, so we have 5. In third group we have 010, 010, and 010 is 2. And in fourth group we have 110, 110 is 6. So 6255 is the octal number that we got from this binary number. And you can say CAD in hexadecimal will give us 6255 in octal. So 6255 is the answer. It's very simple. Now we will move to the next example, the example number 2. And in this example, we want to convert octal number 652, this is in octal, to hexadecimal. In this example, we will reverse the process. First we will convert the octal number to binary. 652 is the octal number, and we will convert it to binary number. And for octal to binary conversion, we have to write 3-bit equivalent binary number for the digits. 6 is written as 110, 110. 5 is written as 101, and 2 is written as 010, 010. So we have converted octal number to binary, and now we will convert binary number to hexadecimal. So 1101011010, this is the binary number, and we will convert it to hexadecimal. We will start from right, and in this case we have to make group of 4 bits. So first group will have 1010, second group will again have 1010, and third group we have 0001. 1010 is 10, and 10 is written as A. 1010 is 10 or A. 001 is 1. So the hexadecimal equivalent of 652 in octal is 1AA. This is the answer. Now we will move to homework problem. I have 2 homework problems for you. In first homework problem, you have to convert the hexadecimal number to octal, and in second homework problem you have to convert the octal number 707 to hexadecimal. So this is all for this presentation. See you in the next one. In this lecture, we will complete hexadecimal to binary and binary to hexadecimal conversion. In hexadecimal number system, we have 16 different digits because base in case of hexadecimal number system is equal to 16. And if you want to find out different digits, it's very simple. 0 to 16 minus 1, which is 0 to 15. So we have 0 to 15 in case of hexadecimal number system. I have already written them, and if you remember, I told you 10 is written as A, 11 is written as B, 12 is written as C, 13 as D, 14 as E, and 15 as F. So this is how we represent 10 to 15 in case of hexadecimal number system. In order to convert hexadecimal to binary and binary to hexadecimal, each one of these digits we have to represent by equivalent 4-bit binary number. Like we did in case of octal number system, we represented 0 to 7 by a equivalent 3-bit binary number. In this case, we will represent them by 4-bit binary number. 0 is represented as 0000. In the same way, we will continue to F, and F is represented as 1111. We will use this table for our conversion. So let's start with it. The first conversion is hexadecimal to binary, and for first example, the hexadecimal number is 259A. This is in hexadecimal, and we want the binary equivalent of this number. From this table you can see 2 is represented as 0010, so we will represent 2 as 0010. 5 is represented by 0101. 9 is represented by 1001, and A, which is 10, is represented by 1010. So binary equivalent of 259A is 0010, 0101, 1001, and 1010. So this is the binary equivalent of this hexadecimal number. Now we will move to second example. The hexadecimal number is CAFE.3D. This is the hexadecimal number, and we want the binary equivalent of this number. We will again use this table. C is represented by 1100, 1100. A is represented by 1010. We have already seen. F is represented by 1111. And E is represented by 1110, 1110. So this is all for the integer part. Now we will move to fractional part. 3 is represented by 0011, 0011. D is represented by 1101, 1101. So the binary number is 1100, 1010. 4 times 1, 1110. then we have point, this is binary point, and after this binary point we have 0011, 0011, 1101. So this is the binary equivalent for this hexadecimal number. Now we will move to the next part of this presentation, in which we will convert binary number to hexadecimal number. In first example, the binary number is 1001.11. So this is in binary, and we want hexadecimal equivalent of this number. We will repeat the same process as we did in binary to octal conversion. First we will locate the binary point, this is binary point, and we will make group of 4 bits. In case of binary to octal, we made group of 3 bits, but in this case we will make group of 4 bits. And for integer part, we will start from right to left. So the first group is 1001, second group will have 1000, and for fractional part we will make group from left to right. So the first group will have 11, and then I will add 2 zeros to make it group of 4 bits. So now we have 3 groups, 2 for integer part and 1 for fractional part. The next thing is to use this table. 1000 is nothing but 8, so we have 8. 1001 is 9, so we have 9. Then we have point, and 1100 is C, so we have C. So 89.C is the hexadecimal equivalent of this binary number. Let's make a small change in this binary number. If I have one more 1 here, then let's see how we have to make the group. I have to add 3 more zeros in order to complete this group, because we need 4 bits and we have only 1 bit. So I will add 3 more zeros to make it group of 4 bits, and this is equal to 1. This is equal to 1. You can see from here 0001 is 1. So the number in hexadecimal is 189.C. Very simple. Adding zeros on the left hand side of the number will not change the number, and also adding zeros on the right side of the number will not change the number. So this is all for binary to hexadecimal conversion. Now we will move to homework problem. I have 2 homework problems for you. In first homework problem, the hexadecimal number is FACE. This is in hexadecimal, and you have to find the binary equivalent of this hexadecimal number. In second homework problem, the binary number is 1101, 1110, 1010, 1111. This is in binary, and you have to find the hexadecimal equivalent of this binary number. So this is all for this presentation. See you in the next one. In this lecture, we will start a new chapter, logic gates. First we will discuss what is logic gate, then we will move to different types of logic gates available to us. So what is a logic gate? It is a physical device which performs logic operation on one or more logical inputs and produces a single logical output. So the first thing is physical device. Logic gate is a physical device and it performs logic operation on one or more logical inputs and produces a single logical output. Very clear. The logic operations like inversion, logical multiplication, logical sum, etc. We can perform them by using logic gate, and we can have one or more logical inputs. For example, in inversion we have only one input, and in logical multiplication we can have 2 or more inputs. So in logic gates we can have one or more logical inputs and it produces a single logical output. So this is a formal definition for logic gates. Now we will categorize logic gates into 3 groups. So let's do it. The group number 1 is basic gates. In this group we have 3 gates. First one is NOT gate, second one is AND gate, and last one is OR gate. Now why we call NOT, AND and OR basic gates? Because we can implement any logic by using NOT, AND and OR. By using these three gates only, we can implement any digital circuit. That's why we call them basic gates. The second one is universal gate. Universal gates. And in this group we have two gates. First one is NAND gate, and the second one is NOR gate. We call them universal gates because by using only NAND or only NOR we can implement any digital system. The last group is arithmetic gates. And in this group also we have two gates. First one is XOR and second one is XNOR. We call them arithmetic gates because we use them in arithmetic operations. We will discuss all these gates one by one, and in this presentation we will start with NOT gate. So let's move to NOT gate. NOT gate. First we will see how we represent NOT gate. Symbol for NOT gate. This is the symbol for NOT gate. A is the input, Y is the output, and Y is equal to A complement. Alright. We can also represent NOT gate like this. Instead of putting bubble at the last, we can put bubble in the front. And the operation will remain the same. Y is equal to A complement. Now we will move to truth table. But first I want to discuss what is truth table. Then we will see truth table for NOT gate. It is the table having outputs from all possible combination of input or inputs. So let me write this down. It is the table having outputs from all the possible combinations of input or inputs. Right? So this is the formal definition for truth table. Now we will make truth table for NOT gate. There is only one input. In case of NOT gate, let's say it is A, and Y is the output, and it is equal to A complement. As there is only one input, we will have two combinations, 0, 1. Complement of 0 is equal to 1 and complement of 1 is equal to 0. So this is the truth table for NOT gate. In the last lecture we completed NOT gate. In this lecture we will complete AND gate. There are points that we have to discuss. First one is symbol, second one is truth table, then we have associative law, commutative law. I will explain all this one by one, and we will start with AND operator. In AND operator, output is high when all the inputs are high. So in AND operator, if you want your output to be 1, you have to make all your inputs equal to 1, and we implement AND operator by using electronic device, and this electronic device we call as AND gate. So AND gate is an electronic device which is used to implement AND operator. First thing in AND gate is symbol. I will make two input AND gate. This is how we represent AND gate. We have two inputs, A and B. This is how we represent output, Y, and Y is equal to A and B. This dot here is AND operator. This is not multiplication, so don't confuse yourself. Now we will make three input AND gate. Let's say the three inputs are X, Y and Z, and the output is equal to F. So F is equal to X and Y and Z. So this is the symbol for AND gate. Now we will move to truth table. I will take 2 input AND gate. So we have A and B, 2 inputs, and output is Y. As there are 2 inputs, we will have 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 combinations, and we have to find out Y depending upon the values of A and B. And as you already know, in case of AND operator, output is high when all the inputs are high. So output Y for first case is equal to 0 because both A and B are 0. In second case also output is equal to 0 because A is 0. In third case output is 0 because B is 0. And in last case output is equal to 1 because both A and B are high. So this is the truth table for AND gate, and this truth table is very important because we will use this a lot in this course. Now we will move to third point, that is associative law. We have to find whether AND gate follows the associative law or not. Associative law says A and B and C equals to A and B and C. On left hand side we will perform AND operation for B and C first, and let's say the result is X. Then we will perform AND operation for A and X. On the right hand side we will perform AND operation for A and B. This will give us Y, let's say, and then we will perform AND operation for C and Y. And if we get equal results, we can say that AND gate follows the associative law. So let's try to prove this. We will prove this by the help of one example. Let's say A is equal to 1, B is equal to 0, and C is equal to 1. First we will solve for left hand side, A and B and C. A is equal to 1, B is equal to 0, and C is equal to 1. 0 and 1 is 0, so we have 1 and 0, and this will give us 0. Now we will solve for right hand side. Right hand side is A and B and C. A is equal to 1, A is equal to 1, B is equal to 0, and C is equal to 1. 1 and 0 is 0, 0 and 1 is 0. So we got the same results for left hand side and right hand side, and we can say that AND gate follows the associative law. Now we will move to fourth point, that is commutative law. Commutative law says A and B equals to B and A, and we have to find whether AND gate follows the commutative law or not. I will take one example. A is equal to 1 and B is equal to 0. First we will evaluate the left hand side, A and B. A is 1, B is 0, so we'll get 0. Then we will find out the right hand side. B is 0, A is 1. This will make no difference. We will get result as 0. So left hand side and right hand side are same. So we can say that AND gate follows the commutative law. So AND gate follows both associative and commutative law. We are done with 4 points: symbol, truth table, associative, and commutative law. Welcome to this part of logic gates. In this part we will discuss OR gate. First we will see what is OR operator. In OR operator, output is high when any one or all inputs are high. So if you want to make output high in OR operation, you have to make any one of your inputs high. We implement OR operation by using OR gate, and in this lecture we will see different properties of OR gate. So let's move to it. First thing that we have to discuss is symbol for OR gate. I will make 2 input OR gate. Y is the output, and I will have 2 inputs. Let's say they are A, B. So Y is equal to A or B. This plus here is OR operator. This is not the sum that we do in mathematics. This is simply OR operator. Now I will make 3 input OR gate. The output is Y, and let's say the inputs are A, B and C. A, B and C. So output is equal to A or B or C. So this is all about symbol for OR gate. Now we will move to truth table, and I will take 2 input OR gate. A, B are the 2 inputs, and Y is the output. It is equal to A or B. As there are 2 inputs, we will have 4 combinations. And for first combination, you can see we have A equals to 0 and B equals to 0. And from this definition, the output is high when any one or all inputs are high. But in this case, A is 0 and B is 0. So we don't have any input equals to 1. So output Y is going to be 0. In the second case, B is high, so output is high. And for third case, A is high, so output is high. And for last case, both A and B are high, so output is high. So this is the truth table for OR gate, and this is very important because we will use this a lot. Now we will move to associative law for OR gate. OR gate follows the associative law, and it says A or B or C is equal to B or C or A. So this is the associative law, and OR gate follows the associative law. You can easily verify this like we did in last presentation. Now we will move to 4th point, that is commutative law. OR gate follows the commutative law, and it says A or B is equal to B or A. Very simple. So OR gate follows the commutative law. Welcome to 4th part of logic gates. In this part we will complete NAND gate and NOR gate. If you remember the first part, I told you we have 3 basic gates, and we have 2 universal gates. The 3 basic gates are AND, OR and NOT, and 2 universal gates are NAND and NOR. This is something we have already covered in first lecture, and by universal gates we mean by using NAND gate or NOR gate we can implement any digital system. On the other hand, we can implement any digital system by using these 3 gates, AND, OR and NOT. And as you can see, NAND gate and NOR gate are not basic gates, so we have to obtain NAND gate by using basic gates, and in the same way we have to obtain NOR gate by using the basic gates. So let's see how we can have NAND gate by using basic gates. We obtain NAND gate by complementing the output of AND gate. So first we have to make AND gate. I will make 2 input AND gate. This is the AND gate. The 2 inputs are A, B, and now we have to complement the output. So I will use one inverter, the NOT gate, and the output Y is A and B and then whole complement. So this is what we have in a NAND gate. This whole unit, including the AND gate and NOT gate, will work as NAND gate, and the output, if we simplify by using De Morgan's law, is equal to A complement or B complement. Now we will try to find out NOR gate, and to obtain NOR gate we have to complement the output of OR gate. So I will make 2 input OR gate. This is the 2 input OR gate. Inputs are A and B, A, B, and now I will use inverter. the output y is equal to a or b and then whole complement. So this OR gate and this NAND gate together makes our NOR gate. And if we apply De Morgan's law, y is equal to a complement and b complement. There is one more way to obtain NAND gate, and in this we will use OR gate and NOT gate. We are not going to use AND gate, but we'll use OR gate. This is the OR gate, and first we will complement the two inputs. So we will use two NOT gates and we'll find the output y. Let's say the inputs are a, b, so we have a complement here, and here we have b complement. So y is equal to a complement or b complement, and you can see we have the same result when we used AND gate and NOT gate. Like NAND gate, we also have another way to represent NOR gate, and we will use one AND gate, and first we will complement the inputs a, b, and the output y is equal to a complement and b complement, which is same. Now we will move to symbol for NAND gate. NAND gate is represented like this, AND gate, and then we have a small bubble at the end. This small bubble represents the NOT gate. These are the two inputs, y is the output. This is how we represent NAND gate, and to represent this arrangement we will first make OR gate, and then we will use two bubbles here, a, b, y is the output, and because of this we also call NAND gate bubbled OR. Okay, now we will move to NOR gate. Symbol for NOR gate, first we will make OR gate, and then we will put a bubble at the end, and this arrangement here is represented like this. First we will make AND gate, we will use two bubbles, a, b, and y the output, and because of this representation we call NOR gate bubbled AND. So this is all for symbol. Now we will move to truth table. First we will make truth table for NAND gate. I will take two input NAND gate, a, b are the two inputs, and y is the output. In truth table for NAND gate, you only have to complement the output of AND gate. So it's very simple. 0 0 will give us 0 in case of AND gate, and complementing 0 will give us 1. 0 1 will give us 0 in AND gate, so again we have 1. 1 0 will give us 0 in AND gate, so we have 1. 1 1 is 1 in AND gate, so here we'll have 0. Or you can simply put the values of a and b in this expression, a complement or b complement. Now we will move to truth table for NOR gate. Truth table for NOR gate, and again we will take two input NOR gate, a, b are the inputs, y is the output. 0 0 0 1 1 0 1 1. If you remember the last presentation, we obtained the truth table for OR gate, and the output y was 0 1 1 1, and we have to complement it. So complementing these values, we have 1 0 0 0. So this is the truth table for NOR gate. Next point is associative law. Only two logic gates does not follows the associative law, and they are NAND and NOR. The universal gates does not follows the associative law. and commutative law is followed by both of them. NAND gate follows the commutative law and NOR gate also follows the commutative law. You can easily prove them. In the last lecture, we completed NAND and NOR gates. In this lecture, we will complete exclusive OR gate. Exclusive OR is also called as XOR. This EX is taken from exclusive and this OR is taken from OR. In order to make this name shorter, we call it XOR. EX also sounds like letter X, so we'll call it XOR. This lecture is very important because if you are expecting questions from logic gates in your competitive exam, then this lecture will really help you. The first thing that we have to complete is symbol of XOR gate. First we'll make symbol of OR gate. This is the symbol of OR gate, and we'll modify the symbol like this. So this is the symbol of XOR gate. Let's take two inputs A, B. The output is Y. So Y is equal to A XOR B. Now there is one thing that you should notice, the representation of XOR. If you remember the OR gate, we represented OR symbol like this, A or B, simple plus sign, but in case of XOR we will put this plus sign inside the circle. So this is the symbol for XOR gate, and this symbol here is traditional symbol. We also have symbol from IEEE, so let's make the IEEE symbol of XOR gate. First we have to make one square, and inside this square we'll write equals to 1. Two inputs are A and B, A, B, and this is the output Y. This symbol is IEEE symbol. Let me write this down, IEEE symbol. So this is all for symbol of XOR gate. Now we will move to internal circuit. Let's move to internal circuit, and first we have to find out the expansion of this A XOR B. Then we can easily find out the internal circuit for XOR gate. So next point is internal circuit. A XOR B, if we expand A XOR B, then we have A and B complement, or A complement and B, or we can write A or B and A complement or B complement. So this is the expansion for XOR, and we can easily implement this expression. We need two AND gates. So let's make two AND gates, and these two AND gates will have two inputs. This is A and this is B. For this first AND gate, the second input is B complement, so we will have B complement like this. I will use one NOT gate. Okay, so the output is A and B complement. For the second AND gate, the second input is A complement because we already have B. So I will take A from here, I will use a NOT gate, and this will give me A complement and B. Now we only have to OR them, so I will use two input OR gate. This is the two input OR gate. These are the two inputs, and the output Y is simply equal to A and B complement, or A complement and B. So this is the internal circuit for XOR gate. Now we will move to truth table. The truth table for XOR gate, and this is very important truth table because I will use this truth table a lot. I will consider two input XOR gate. A, B are the two inputs, Y is the output, and as we are having two inputs, we'll have four combinations: 0 0 0 1 1 0 1 1. These are the four combinations, and now we have to find output Y. I will use this expression A and B complement, or A complement and B. We have already implemented this expression in our circuit, and now we'll find out output Y. When A is 0, B is 0, we have A 0, B 0, so B complement is 1, or we have 1 and 0. So output Y is equal to 0 or 0, and finally it is equal to 0. When we have A equals to 0 and B equals to 1, let's see what we have. When A is equal to 0 and B is equal to 1, it means we have 0 and 0, or 1 and 1, because A is 0, so A complement is 1, B is 1, so we have 1. This will give me 0 or 1, and finally 1. So we have 1 as the output for the second case, and in the same way, if you calculate for the last two cases, you will have 1 and 0. Now you can clearly see in this XOR truth table, the output is high. The output is high when we have odd number of ones. In both these cases, we have single 1 which is odd, and when we have even number of ones, the output is low. And because of this, we call XOR gate odd ones detector, odd ones detector. And this point is very important because it will save you time in your exam. You don't have to worry about this expression. You only have to check whether you have odd number of ones in input or not. When you have two inputs, it is easy to find the output by using this expression, but in question, if you have 3, 4 or 5 inputs, it is better to use this property. So this is all for truth table. In this part of logic gates, we will learn exclusive NOR gate. In the last lecture, we completed exclusive OR gate. Exclusive NOR gate is also written as XNOR, or we can write it as XNOR. XNOR gate is obtained by complementing the output of XOR gate. So first we will make XOR gate. I will make two input XOR gate. This is the symbol of XOR gate. The two inputs are A and B. The output of this XOR gate will go to this inverter, and the output of this inverter is the output of the XNOR gate, and it is equal to A XNOR B. This is the representation for XNOR. In case of XOR, we have plus inside the circle, and in case of XNOR, we have a dot inside the circle. Now we will move to symbol. Symbol of XOR gate. First we will make this symbol of XOR gate, and to represent this inverter, I will put a small circle at the end of XOR gate, or we can say bubble at the end of XOR gate. A, B, output is Y. This symbol is traditional symbol. This symbol is traditional symbol for XNOR gate. We also have IEEE symbol for XNOR gate. It looks something like this, equals to 1, and then I will place a small bubble, the two inputs and the output. This symbol is IEEE symbol. IEEE symbol. Now we will move to truth table. The next thing is truth table. Let's make truth table for 2 input XNOR gate. The two inputs are A, B, output is Y, 0 0 0 1 1 0 1 1. These are the 4 possible combinations. Now there are 2 ways to find out the output Y. It is equal to A XNOR B, and we have to expand this. The expansion is A and B, or A complement and B complement. Now you can simply put the values of A and B in this expression and you will have your output Y, or we can simply complement the output of XOR gate. If you remember the table from the last presentation, you can simply complement it and you will have the output Y. But I will use this expression to find out Y. A is 0, B is 0. So we will have 0 and 0, or 1 and 1. So 0 or 1, and this is equal to 1. So we have 1 here, and in the same way we will have 0 0 1. So this is the truth table for XNOR gate, and you can see when A is equal to B, output is equal to 1. When A is equal to B, output is equal to 1. And when A is not equal to B, output is equal to 0. For these 2 cases, A and B are different and output is equal to 0. XNOR follows the commutative and associative law. The next point, XNOR follows the commutative and associative laws. This is important point. In this lecture, we will discuss why NAND is called as universal gate. In the first lecture of logic gates, I told you we have 2 universal gates, NAND and NOR. We call them universal gate because we can implement any digital system by using NAND or NOR. Now I have to prove this statement. NAND and NOR are called as universal gates, and for this we will first revise basic gates. We have 3 basic gates, AND, OR and NOT. AND, OR and NOT are sufficient to implement any digital system. We can implement any digital system by using AND, OR and NOT. And if we can convert NAND or NOR to these 3, if we can convert NAND or NOR to AND, OR and NOT, we can say that any circuit can be implemented by NAND or NOR alone. This is very simple. We can implement any digital system by using basic gates, AND, OR and NOT. And if I can convert NAND to NOT, NAND to AND, and NAND to OR, if I can convert NAND to this 3, I can say that NAND is universal gate. Because by using these 3 we can implement any digital system, and as we can have NOT, AND and OR, by using NAND only we can implement any digital system by using NAND only. And the same thing is applicable for NOR. In this lecture we will deal with NAND gate. In the next lecture we will deal with NOR. First I will implement NOT gate by using the NAND gate. Let's take 2 input NAND gate. The output Y is equal to A and B and its whole complement. If we have 2 similar inputs, then output Y is equal to A and A. This is the first input, this is the second input, and its whole complement. A and A is equal to A. So finally we have A complement. So if we provide same inputs to the NAND gate, it will work as NOT gate. It will work as NOT gate if inputs are same. Very simple. So first we will make 2 input NAND gate. These are the 2 inputs and this is the output Y, and if the 2 inputs are A, let's say, then the output Y is A complement. So this is working as NOT gate. If the input is A, the output is A complement. Very simple. Now we will implement AND gate by using the NAND gate. And if you remember the NAND gate presentation, I told you we obtain NAND gate by complementing the output of AND gate. If we have AND gate, and if we complement the output of AND gate, then this will work as NAND gate, A and B and its whole complement. This is something we have already discussed, and now we want the AND gate back. We want our AND gate back. So only thing we have to do is to complement the output of NAND gate. If you complement the output of NAND gate, you are going to get AND gate, because complement of A complement is equal to A. Very simple. So let's do this. First we will make NAND gate. I will make 2 input NAND gate, A, B, and the output Y, let's say it is Y prime, and it is equal to A and B and its whole complement. We want AND gate, so I will complement the output of NAND gate. Y is equal to A and B and its whole complement, and again we have complement. So finally we are going to get A and B, and A and B is what? AND operation. So this is how we can have AND gate by using the NAND gate, but we can only use NAND gate. So this NOT gate must be replaced by this circuit. So let's implement it quickly. This is the NAND gate A, B, and I will use one more NAND gate with 2 similar inputs, and this one here will work as NOT gate, and the output Y is equal to A and B, and the combination of 2 NAND gates are working as AND gate. Now we will move to implementation of OR gate by using the NAND gate. Output of 2 input NAND gate is A and B and its whole complement. If you simplify this by using the De Morgan's law, you will get A complement or B complement, and OR operation is like this. So what we need to do, we only have to change this A complement to A and this B complement to B. So we can simply complement the inputs before giving it to the NAND gate. So we will complement the inputs. We will complement the 2 inputs first, A, B. So we have A complement, B complement, and then we will feed them to the NAND gate. So the output Y is equal to A complement and B complement and its whole complement. By using the De Morgan's law, Y is equal to A or B, which is OR operation. So this is how we can implement OR gate by using the NAND gate, and again we will do the same thing. I will replace this NOT gates by the NAND gate having the 2 similar inputs. So we have to use 3 NAND gates to implement OR gate. We have to use 3 NAND gates to implement the OR gate, and to implement NOT gate, 1 NAND gate is required, 1 NAND gate is required, and to implement AND gate, 2 NAND gates are required. The next thing is implementation of NOR gate, but before this I would like to tell you that we have already proved that NAND is universal gate, because we have implemented the NOT gate, we have implemented the AND gate, and we have implemented the OR gate. We have already implemented the 3 basic gates, AND, OR and NOT, and we have done this by only using the NAND gate. So NAND is universal. We can implement any digital system by using the NAND gate. Now we will implement the NOR gate, and NOR gate is obtained by complementing the output of OR gate. If this is the OR gate, then we have to complement the output of OR gate to get the NOR gate. So in this circuit we have to complement this output Y. So let's do this quickly. This is very simple. First I will use two NAND gates acting as inverters. A, B are the two inputs. Then we will use another NAND gate whose output is equal to A or B, and then I will use another NAND gate working as inverter, and the output Y is equal to A or B and its whole complement, and this is NOR operation, right? So to implement NOR gate, we require 4 NAND gates. To implement NOR gate, we require 4 NAND gates. Now we will implement XOR gate by using the NAND gate. This is very important implementation. You can consider this as an example of implementing logic functions by using the NAND gate. So first thing that we have to see is the number of NOT, AND and OR gates. To implement B complement and A complement, we need 2 NOT gates, and to implement A and B complement, A complement and B, we need 2 AND gates, and finally we require one OR gate. And as I have already explained, in case of NOT gate we require one AND gate, in case of AND gate we require 2 NAND gates, and in case of OR gate we need 3 NAND gates. So let's try to calculate how many NAND gates we require to implement the XOR gate. For NOT we require 2 NAND gates, one for each. For AND we require 2 NAND gates, and we have 2 AND gates, so we'll have 4 NAND gates. And for OR we need 3 NAND gates because we only have one OR gate. So in total we require 9 NAND gates to implement XOR gate. So let's do it quickly. First we will implement the 2 NOT gates. So we will make 2 NAND gates, and we will provide similar inputs to these 2 NAND gates so that they work as NOT gate. This is A, this is B, and now we will implement the 2 AND gates. Okay, the output of AND gate is A and B complement, so we will take A from here, and this will act as input for this NAND gate. So the output here is A and B complement, and for the second AND gate A complement and B is the output, so we will take B from here, and the output here is A complement and B. So you can clearly see these 2 NAND gates, and these 2 NAND gates are working as AND gate, and this NAND gate here and this NAND gate here are working as NOT gate. So we have implemented the 2 NOT gates and 2 NAND gates. The only thing that we have to do is to implement one OR gate. So I will implement one OR gate, and for this we require 3 NAND gates. First we will use 2 NAND gates as inverter, and then we will use the third NAND gate to get the output of OR gate. So let's do this quickly. First we will have inverter, and this is Y, the final output, and it is equal to A and B complement or A complement and B. You can easily prove this. This gate is working as NOT gate, and the input is A complement and B. So we have output as A complement and B and its whole complement. In the same way, here we have A and B complement and its whole complement. Here Y is equal to A complement and B, its whole complement, and A and B complement and its whole complement, and finally we have complement of all. We will use De Morgan's law to simplify this. Y is equal to A complement and B, or A and B complement. This is A XOR B. So we have implemented the XOR gate by using the 9 NAND gates, and this is not the best way, to implement the XOR gate. We can implement XOR gate by using 4 NAND gates only, and here we are using 5 extra NAND gates. So let's see what is redundant in this circuit. We are using NOT gates like this, and if you use NOT gates in this manner, let's see what we have. If A is the input of this NOT gate, here we'll have A complement, and finally we will have A again. So we are getting the same function by using the 2 NOT gates in this manner. So there is no need to use this 4 NAND gates. We can eliminate this 4 NAND gates from this circuit, and will still have the output equals to A complement and B, or A and B complement. So we have reduced 4 gates from 9, and now we are using 5 NAND gates to implement XOR. But still we have to get rid of 1 NAND gate because it can be implemented by using 4 NAND gates. So let's see what we can do. First I will make this circuit again, and now I won't include this 4 NAND gates. This is A, this is B, and I'm not going to use this 2 NAND gates. So the output of this NAND gate will go to this NAND gate here. In the same way, output of this NAND gate will also go to this NAND gate, A and B. So we are using 5 NAND gates. At this point we have A complement and B and its whole complement, and at this point we have A and B complement and its whole complement. We are getting this too by using 4 NAND gates, but we have to obtain these results by using 3 NAND gates. Here we are using 4 NAND gates to obtain this too, but we have to use 3 NAND gates. So let's see how we can have the same results by using the 3 NAND gates. First I will draw it and then I will explain. This implementation is very important. Y is equal to A XOR B. So instead of using the 4 NAND gates, now we are using 3 NAND gates in this manner, A, B. Now we will check whether we are getting these 2 results or not. Output of this NAND gate is A and B and its whole complement. Output of this NAND gate is A and B, its whole complement, and finally the complement of all. In the same way, here we'll have this, and now we have to simplify this. So let's do this quickly. I will use the De Morgan's law. A complement or A and B. Here we'll have B complement or A and B. And if you remember the Boolean algebra, I told you if we have X complement or X and Y, it is equal to X complement or Y. In the same way, from here we'll get A complement or B, and from here we'll get B complement or A. A complement or B can be written as A and B complement and its whole complement, and B complement or A can be written as A complement and B and its whole complement, and you will find we have the same results, A complement and B and its whole complement from here, and A and B complement and its whole complement from here. So we can say that this is the most efficient implementation. This is very important because you have to use your brain to get this circuit. We started from this circuit, we had 9 NAND gates, then we had this circuit with 5 NAND gates, and finally we have this circuit with 4 NAND gates. So this is the most efficient implementation, and please draw it somewhere so that you can revise it before your exam. Now we will move to XNOR implementation by using the NAND gate, and you already know to obtain XNOR we complement the output of XOR gate. We complement the output. If A and B are the two inputs, then output Y is equal to A and B, or A complement and B complement. So implementation of XNOR gate by using the NAND gate is very simple, and this will require 4 NAND gates. So first we will make XOR gate by using 4 NAND gates, and then to complement the output we will use one inverter, and this will require 1 NAND gate. So 4 plus 1 is equal to 5 NAND gates. 5 NAND gates are required to implement the XNOR gate. So this is all for this lecture. Now in the last 2 lectures we have completed NAND as universal gate. In this lecture we will do the same thing for NOR gate. We already know there are 2 universal gates, NAND and NOR, and we call them universal gate because we can implement any digital system by using any one of them. And to prove this we have to implement basic gates and OR and NOT. These 3 are the basic gates, and we have to implement them. We have to implement AND gate, OR gate and NOT gate by using NAND or NOR. We have already completed this part. We have implemented the basic gates by using the NAND gate in the last 2 presentations. In this lecture we will implement them by using the NOR gate, and if we can implement them by using the NOR gate, we can say that NOR is universal gate. So we will quickly move to the implementation part. First I will implement NOT gate by using the NOR gate. If we have 2 input NOR gate, then output Y is equal to A or B and its whole complement, because NOR gate is obtained by complementing the output of OR gate, and in case of OR gate output is equal to A or B, and when you complement this you will get A or B and its whole complement. And if we have 2 similar inputs, then output Y is equal to A or A and its whole complement. This is the first input, this is the second input, and finally we will have a complement. So NOR gate will operate as NOT gate if we provide the same inputs to the gate. So we'll quickly implement it. First I will make 2 input NOR gate. A is the first input, Y is the output, and the second input is also A. So output Y is equal to A complement. So this is the implementation of NOT gate by using the NOR gate. Now we will implement OR gate by using the NOR gate, and as I have already told you, we obtain NOR gate by complementing the output of OR gate. If this is OR gate, if this box represents the OR gate, 2 input OR gate, and if we complement the output of this OR gate, so this combination will work as NOR gate, and we want our OR gate back. So we will again complement the output of NOR gate. This is the output of NOR gate, so we will again complement it to get the OR gate. This is very simple and you can easily implement this. First you have to make the NOR gate. The 2 inputs are A, B, and the output we have to complement. and we'll use NOT gate for this purpose. But as we have to use only NOR gate for our implementation, so instead of using the NOT gate, we will use this arrangement. So I will use another NOR gate with similar inputs. This will work as NOT gate, and the output Y is equal to A or B, its complement, and complement again. Simplifying this by using the De Morgan's law, we will have A or B, which is OR operation. So we can have OR gate by using the two NOR gates like this. Let me write this down. We will use two NOR gates to implement OR gate, and we will use one NOR gate to implement NOT gate. The next implementation is implementation of AND gate by using the NOR gate. So let's do this quickly. If I have two input NOR gate, with the two inputs equal to A, B, then the output Y is equal to A or B and its whole complement. If I simplify this, then output Y is equal to A complement and B complement. We have done this by using the De Morgan's law. And if we want to have the AND gate by using the NOR gate, what we can do? We can complement this A complement and we can complement this B complement. Let's do this. Complementing A complement, we have A, and complementing B complement, we have B. So we have A and B, the AND operation, if we complement the two inputs of NOR gate. So we'll do this quickly. We will complement the two inputs, and again I will use this arrangement here, because we are implementing the gates by using the NOR gate only. First I will complement A. So let's make one NOR gate here, and the two inputs to this NOR gate are A. So here we will have A complement, right? Then I will complement B, and the two inputs are B. So here we will have B complement. Let's check what we have as the output of this combination. The output Y is equal to A complement or B complement and its whole complement. By using the De Morgan's law, we have A complement, its complement, and B complement, its complement, and this will give us A and B, which is the AND operation. So this is how we obtain the AND gate by using the three NOR gates. So we require three NOR gates to implement the AND gate, and you can see we have implemented the three basic gates, AND, OR, and NOT. So we can say that NOR is universal gate. We can implement any digital system by using the NOR gate only. Now we will implement the NAND gate. And it's very simple, because NAND gate is obtained by complementing the output of AND gate. We have already implemented the AND gate like this, so we only have to complement the output of this arrangement. First we will complement the input A, then we will complement the input B, and the output of this NOR gate and this NOR gate will act as the input of this NOR gate. Okay, so this is our AND gate, and now we have to complement the output. So for this we'll again use the NOR gate with common inputs. Here we have A and B and its whole complement, because we have already proved output of this arrangement is A and B. From here you can see, and if we complement this, we will get A and B and its whole complement. So we need 1, 2, 3, 4 NOR gates, 4 NOR gates to implement the NAND gate. The next implementation is implementation of XNOR gate. I'm not going to explain this much because we have already done this for XNOR gate by using NAND gate only. In the last presentation we have already completed this. So I will simply make the circuit and we will check whether it is working as XNOR or not. And if you want the detailed discussion on it, then you can see the last presentation how we implemented XOR by using the NAND gate. You have to follow the same steps. So first I will make the circuit and then we will check for the output. Four NOR gates are required to implement XNOR gate. And if you remember the last presentation, 4 NAND gates were required to implement the XOR gate. And this implementation is very important. A and B are the two inputs. So this is how you can have XNOR gate by using the four NOR gates. Now we will try to prove the output Y is equal to A and B, or A complement and B complement, which is A XNOR B. First we will find out output of this NOR gate. We have A or B and its whole complement. Now we will find output of this NOR gate. We have A or B and then complement of all. Similarly here we'll have B or A or B, its complement, and then complement of all. Now you have to simplify this. So we'll do this quickly by using the De Morgan's law. A complement and A or B, and here we'll have B complement and A or B. You can open this or you can simply move to find out the output of this final NOR gate. So I will find out the output of this final NOR gate without simplifying them further. So we have A complement and A or B, or B complement and A or B, and then complement of all. Again we will use De Morgan's law, and this will give us A complement and A or B, complement of all, and B complement and A or B and complement of all. Again we will use De Morgan's law, A or B and its complement, and B or A or B and its whole complement. Right? Now we can take A or B, its whole complement, as common. So we will have A and B, or A or B and its whole complement. Finally we will have A and B, or A complement and B complement, and this is equal to A XNOR B. So we can say that this arrangement with 4 NOR gates is working as XNOR gate, and if you want to implement XOR gate by using the NOR gate, then you have to complement the output of this arrangement. So we'll quickly copy this arrangement. I will copy this and then we'll paste it. And the output of this arrangement we have to complement. We have to complement the output, and the output Y here, let's say it is Y prime, is equal to A XOR B. So by using 5 NOR gates, we can implement XOR gate. This is very much similar to the last presentation. We have done this for XOR and XNOR by using the NAND gate, and in this lecture we have done this for NOR gate. I think it is clear to you how to implement all the other gates by using the NAND and NOR. In this presentation, we will try to find out the answer of the question, what is parity? I think this word parity is something that you are already familiar with, because it is something which very often repeated in the digital electronics course. So let's move to it. It is concept to detect the errors. Error detection and its elimination is a very vast field in the electronics, and the engineers and scientists constantly work on this field, because we want the signal transmitted as it is at the receiver's end. We do not want any distorted signal at the receiver's end. So the parity is one way to detect the errors, and it is only for the detection of a single bit error. Okay, a single bit error is detected by it. If there is an error in the 2 or more bits, then definitely the parity is not going to tell you about the error, because it is only for a single bit error. Now I will explain you these two things in a real quick time, and let's move to it. Let's say this is our receiver's end. Okay, this one is our receiver end, Rx, and the yellow one is our transmitter end. This is our transmitter's end. And a signal is transmitted from, let's do it in different color. A signal is transmitted from the transmitter to receiver. Generally we make transmitter on this side, but I made it, so there's no problem. A signal is transmitted through this channel from the transmitter and then received by the receiver. Let's say the signal is a 4-bit signal. Okay, and we know that in this channel there are so many factors that are there to affect this transmitted signal. So there are noises involved, and because of that noise, maybe some bits changes from 0 to 1 or 1 to 0. We can say that it becomes high to low or low to high, and if that happens, we can detect it by the parity. So what is this parity? This parity is actually an extra bit. Let me write it down. It is an extra bit that we send with the bit stream. So we send a bit stream, which is this 4-bit signal, and also an extra bit, and this extra bit tells us the total number of ones. Tells us the total number of ones in the transmitted signal. So what is the use of this total number of ones? So this is something we have to cover by one example, and let's say in this 4-bit signal, transmitted signal, we are having a single one. So let me write it down, 0 1 0 0. This is the transmitted signal, let's say. Now you can see the number of 1 in this bit stream is 1, which is of course odd, and if it was even, then we have to do the different operations. So depending upon this, there are two types of parity. The first one is your even parity, and the second one is your odd parity. Okay, now if we are talking about the even parity, so what will happen? An extra, this is our original transmitted signal, and there is an extra bit that will tell us about the total number of ones, and we call it as the parity bit. This is our transmitted signal, or you can say that original signal, and here we are having the parity bit. Okay, and whenever we are talking about the even parity and there is an odd number of 1 involved in the original signal, we will add a 1 here in the parity bit, or we will make the parity bit high to make the total number of 1 as even. Remember, the total number of 1 as even, because this is a bit confusing. People think that whenever there is a even ones in the original signal, we will make the parity bit high, and that is actually we do in the odd parity. So what you have to remember? You have to remember that in the overall signal, the number of 1 should be even in case of even parity. Very simple. Let's take another example of this even parity. If this signal, the original signal was 1 1
0 0. So what you can see here, you can see that there are two ones, which means it is even number of ones. So whenever there is an even number of ones already, in case of even parity, we just make the parity bit 0, because what we want at the end of the day, we want the number of 1 as even in case of even parity. Similarly, if we talk about the odd parity, this was the case of even parity, and now we will talk about the odd parity, and we will take one example of a 4-bit original signal. The same example, let's say 0 1 0 0. Okay, this is our original signal, and here we are having the parity bit. So in case of odd, we want the overall signal including this parity bit odd number of 1. So here we are already having the odd number of 1, so we will add just 0 as the parity bit. And let's take this one. In case of odd parity, 1 1 0 0, here we can see that the number of 1 is even, and in odd parity we want the total number of 1 as odd, so we will add 1 here. So this is very simple, but how we are going to detect the error now? We just right now we know that what we have to do in the parity, we just add another bit stream, or you can say that the extra bit, not a bit stream, extra bit, which tells us about the total number of ones, whether they are even or odd. Now how we are going to use this information for the error detection? Let's say in this particular case, a noise has been added. A noise has been added in the channel, and because of that noise, let's say this 0, this last 0, that is our LSB, becomes 1, which was actually 0 in the previous case, and this parity is set at the transmitter's end. And this parity is already set as 1 depending upon the signal 0 1 0 0, but now because of the noise, the last 0 is now 1. So we already know that it is the even parity. The transmitter end has to inform that the receiver end that we are sending the signal according to the even parity. So he will detect the signal and he will see that the parity bit is high, which tells us that there must be an odd number of 1 in the original signal. But what we are having here, we are having even number of 1. So definitely at the receiver end, he will know that there is an error. There is an error in this particular signal. Okay, so this is how we detect error in the parity. I think this is clear to you.